Hello everyone, this is Vrishali Edlabadkar and we are going to see a video for differentiation under integral sign. As we say, differentiation under integral sign, its differentiation under integral sign is DUIS, that means we are differentiating under integral sign. Now, we are differentiating under integral sign. That means if we have an integral, let us say it's I of alpha equal to integral a to b f of x comma alpha dx. Here a to b, these are limits of integration, or here we say these are constant but they are functions of parameter alpha. Now your integrand f, it is function of x and alpha. That means x is variable and alpha is any parameter. Now we are going to see what is Leibniz rule for differentiation under integral sign. Differentiation under integral sign, that means we are differentiating this I with respect to alpha. Let us remember this alpha is our parameter. So di by d alpha is equal to integral a to alpha delta by delta alpha of f of x comma alpha dx. F of x comma alpha dx. We are differentiating partially with respect to alpha. And this x here is going to be constant when we are differentiating with respect to alpha. Okay. Plus f of b comma alpha. Your integrand is f of x comma alpha. Now here what we are writing is f of b comma alpha. db by d alpha. That means d by d alpha of what is our b? B is nothing but upper limit minus f of lower limit comma alpha dA by d alpha. F of lower limit comma alpha d by d alpha of lower limit a. This is Leibniz rule for differentiation under integral sign. Let us now see an example. If I of alpha is equal to integral a to b f of x comma alpha dx, where a and b are constants. Now what we are saying is if a and b are constants which are free from alpha, that means they are not functions of parameter, then what will happen is these two terms are going to be 0 because b and a both are free from alpha and we are differentiating with respect to alpha. If it is a constant, if it is free from alpha, then the derivative is going to be 0. And hence, if these limits are free from alpha, in that case, your Leibniz rule will only be this much. Right? Now, here we have integral 0 to 1. We need to show integral 0 to 1 x to the power a minus 1 log x is equal to log of a plus 1. Now, here your limits are 0 and 1. Right? Your function is x to the power a minus 1 log x. That means f is function of x comma alpha. X is your parameter. Sorry, x is your variable and a is parameter. So I'm writing I of a is parameter, is equal to integral 0 to 1 x to the power a minus 1 log x dx. Di by dA is equal to integral 0 to 1. Now we are differentiating with respect to a. When we are bringing or when we are differentiating this integral, that derivative becomes partial delta by delta a of this function x to the power a minus 1 log x. Derivative of x to the power a minus 1 log x, it will be equal to x to the power a into log x. Derivative for log x is going to be, actually log x is a constant. Derivative for this one is going to be 0. So what will remain with is only 0 to 1 x to the power a dx, as this log x and one more log x from derivative of x to the power a is getting cancelled. So now di by dA is equal to 1 upon a plus 1 after putting the limits of integration. Okay. Integrating that, what we got is I of A is equal to log of A plus 1, log of A plus 1 plus C. This C is any arbitrary constant. Now, at A equal to 0, at A equal to 0, this log of A plus 1 will be 0. And I of A at A equal to 0 will again give you 0. Hence, we will get C is equal to 0. Therefore, I of A is equal to log of A plus 1, which was to be proved. Okay. Now, let us go for an example where we have limits as functions of parameters. Now, here our question is prove that phi of A is equal to integral pi by 6a to pi by 2a sine of ax upon x dx is independent of A. Okay, that means we need to show that this phi of A is independent of A. Now, if we are showing that d phi by dA is equal to 0, if we are showing d phi by dA is equal to 0, that means your phi is free from A, phi is independent of A, then and then only derivative of that phi with respect to A will be 0. So let us use DUIS for finding d phi by dA. So d phi by dA will be equal to, now just remember here our limits are functions of A. So phi by 6a to pi by 2a, dabba by dabba a of integrand. What is your integrand? Sin ax upon x dx plus function of upper limit comma parameter. Upper limit is pi by 2. Parameter is a. So it's sine of a pi by 2a upon pi by 2. D by dA of pi by 2 minus sine of a pi by 6a lower limit upon pi by 6a d by dA of pi by, read this as pi by 6a. So integral pi by 6a to pi by 2a, dabba by dabba a of sine x by x is going to be cos x by x, and derivative of this cos x, derivative of this ax is going to be x. So this x and x are getting cancelled. We will then remain with, or then we'll integral cos, get integral of cos ax and putting the limits. So your dabba phi by dabba a, sorry, d phi by dA will be equal to 1 by a sine pi by 2 minus sine pi by 6. Integral of cos is going to be sine ax from pi by 6a to pi by 2a will be equal to 1 by a sine pi by 2 minus sine pi by 6. This is for integration, upper limit minus lower limit. Apart from this, we have these two terms minus 1 by a and plus 1 by 2a. These two are as it is. So 1 by a sine pi by 2 is 1 minus sine pi by 6 is half minus 1 by a and plus 1 by 2a. Hence overall what we got is entire term is going to give us 0. This implies that d phi by dA is going to be 0. That means your phi, it is independent of A, which is what we have to prove. What we have proved is d phi by dA is equal to 0. That means phi of A, it is independent of A, right? Let's go for another example. Now here we have f of x is equal to 2 to x minus t, g of t dt. Now here we need to prove that d2f by dx square minus g of x is equal to 0. Okay, now what we have here is f of x is integral 2 to x. Look at those limits. Limits are from 2 to x. That means here your limits are functions of parameter. Fine, 2 is constant, but x is a function of parameter. X is parameter and t is variable for this question. So 2 to x, x minus t, g of t dt. We need to prove that d2f by dx square minus g of x is equal to 0. That means we have to apply differentiation under integral sign twice. As we can see d2f by dx square. That means we are applying dys two times for getting this equation, this differential equation. Okay. Now using dys. Now we are using dys, but our limits are functions of parameters. So we need to write it as df by dx will be equal to 2 to x deva by deva x. Remember when we are bringing integral differentiation under this integral sign, it becomes a partial derivative with respect to x. We need to remember here t is variable and x is parameter. So deva by deva x of x minus t g of t dt plus f of upper limit comma parameter. Upper limit is x. So x minus x g of x d by dx of upper limit. Alright. Minus lower limit comma x function of lower limit comma parameter. Parameter here is x. We are simply replacing t by 2 because lower limit is 2. X minus 2 g of 2 d by dx of 2. Alright. Now, when we are differentiating this x minus t g of t partially with respect to x, t is constant. So g of t is a constant. Derivative of x minus t is going to be 1. So we'll get integral 2 to x g of t dt because x minus t on differentiating partially with respect to x will give us 1. This term x minus x will give you 0 minus x minus 2 g of 2, but then d by dx of 2 will give you 0 once again. Hence, this entire term is now only be integral 2 to x g of t dt. So what we got is df by dx is equal to integral 2 to x g of t dt. Okay, so we have applied DUIS when your limits are functions of parameter ones. But what we need to prove, it demands that we need to differentiate once again. That means we need to apply differentiation under integral sign once again. Right? So once again differentiating this df by dx with respect to x. X is our parameter. Remember, we are differentiating with respect to parameter. So d2f by dx square will be equal to integral 2 to x deva by deva x of g of t dt plus what your function now is integrand is g of t. So g of upper limit d by dx of upper limit minus g of lower limit d by dx of lower limit. Is that clear? G of x is our integrand now. Okay. Now deva by deva x of g of t. This g of t, it is function of t only. Function of a single variable t. And we are differentiating it partially with respect to x. So its partial derivative with respect to x is going to be 0. Hence we got 0 for this first term. Second term is g of x, deva by x of x. Deva by x of x will give you 1 and g of x will remain as it is, minus g of 2, fine as it is, but d by dx of 2 will give you 0. Hence we got 0 plus g of x minus 0. Ultimately, we are only remained with d2f by dx square is equal to g of x. Or we may say that d2f by dx square minus g of x is equal to 0. Okay. So we just need to remember that when we are applying differentiation under integral sign, the very first thing what we need to check is whether the limits of integration they are constants or they are functions of parameter. If they are constants, then derivatives of limits with respect to parameter are going to be 0. So in Leibniz rule, we'll only come across first term. But if limits are not constant, those are functions of parameters, then we are going to apply entire Leibniz rule for differentiation under integral sign as this one. Okay. I hope you got, I have explained here 3 examples for differentiation under integral sign. Enjoy learning. Have a good day. Thank you.